All right. So now if I look at this learning with error problem, what happens if I take the simplest case? So again, I'm going to take this simple group, Z mod Q. So it's equivalent to choosing m numbers uniformly at random mod Q. And I would need to recover a hidden integer given these integers and randomized approximation of S times G1 mod Q, S times G2 mod Q, and S times GM mod Q. Okay? So this is just the special case of learning with errors if I take this group. Okay? So what is funny is that this problem was actually studied by cryptographers almost 10 years before LWE. So Bonnet and Venke studied the so-called hidden number problem. They introduced this problem, and that's that Crypto 96 paper. So what I said is that this is the theorem of Regev. So Regev proved in 2005, and that got him the Gödel Prize many years later. So he showed that if you can solve this LWE problem on the average for the same group as ITI, then again, you can solve a hard lattice problem for every lattice, so find short vectors in any lattice. But there is a catch. You cannot solve it on a normal computer. You can only solve it with a quantum computer. Okay? So it's really the analog of ITI's result, except that the reduction is quantum. Okay? And again, same as ITI's result can be generalized, Regev's results also generalize to any sequence of finite abelian groups, provided that the order grows sufficiently fast. Okay?
So it's much less powerful to be able to solve it quantum efficiently than just standard efficiently.
Yes. So you have to believe, if you want to use it, you have to assume that this problem remains hard even for quantum computers. So that's of course a stronger assumption. However, it's also more powerful because this problem is much easier to use for cryptographers. Okay, so after that, if you assume that this problem is hard on the average, there's many more things you can do in cryptography. For instance, you can do what we call homomorphic encryption based on this. Fully homomorphic encryption is possible with this, but not with the other problem. Okay. All right, so enough about this. So I introduced these lattice problems, and we saw some randomized version of these lattice problems. And we saw some hardness results associated to it. Now it's time to talk about the LLL algorithm. And even though many of you already know the algorithm, there's going to be something that maybe you're not aware of. So my story will start with Hermite inequality. So remember in 1850, Hermite showed an exponential bound on Hermite constant. Okay, so you can see, you can write inequality like this. It relates the d-dimensional constant to the two-dimensional constant. Okay. So it's telling you that in any lattice, there is a non-zero lattice vector of norm less than something related to this times the diff root of the volume. So you can view LLL as a constructive version of that inequality. So it gives you a non-zero lattice vector of exactly the same bound modulo some epsilon. Okay? So it's really an algorithmic version of Hermite inequality. Okay. So you give to LLL any basis of the lattice, it gives you a vector below that bound. Okay, provably. Okay, so now I want to see how it works. So when I got interested into this connection with Hermite's work, I looked at, I read the original letters of Hermite. So it was not really an article, it was a letter a private letter to Jacobi. And if you summarize Hermite's argument, it's really an inductive proof. And the proof goes as follows. So it's obvious for d equal to 1. In high dimension, what you do is you take a shortest vector. You consider a shortest vector of the lattice. And you're going to project over the hyperplane of orthogonal to B1. Okay? So you consider the projection of the lattice. So if you, in general, when you project a lattice over a hyperplane, it may not be a lattice. It may not be discrete anymore. However, if you project over a hyperplane orthogonal to a basis vector, it is a lattice. It is discrete. So you can, this is a lattice. So let's consider a shortest vector of this projected lattice and call it pi of B2. Okay? So pi of B2 is a projected vector. What can you say about B2? Well, we have some flexibility of B2 because we're working modulo B1. So you can see that by choosing the right lift of pi of B2, I can always make sure that the norm of B2 is not too much compared to the norm of the projection plus some factor depending on B1. Okay, so I'm just limiting the component of B2 over B1. Okay? And because B1 is the shortest vector, I know that B1 is less than B2. And I know also the volume of the projection is related to the volume of the initial lattice and the norm of B1. So if I break everything together, if I use Hermite inequality on pi of B2, I use this, I plug it everywhere, I obtain that B1 is less than Hermite's bound. Okay, so that's Hermite's proof. Okay. So is the proof constructive? So I'm asking you, does it give you a non-zero lattice vector satisfying Hermite's inequality? So what do you think? Is this proof constructive for you? No, why?
Because the first line is that's
yeah. Yeah, so that's bad. I mean, you're starting with the solution, so that's bad. However, if you're a little bit more flexible, you could say, okay, what if it's not the shortest vector? What if we start with an arbitrary basis, and B1 is my first vector? Can I use the same ideas to maybe find a shorter vector than B1? Right? So yes, I agree. The initial proof is not constructive. However, if I play a little bit, if I'm a bit more flexible, if I start with a primitive vector, I can play the same game and say, OK, B1 for now is not the shortest vector. But I can still project. I'm still allowed to do that. Let's assume that I have found, by induction, a nice vector, a short vector in the projection. But I'm applying the same argument. So again, I'm going to limit the size of B2 using the same thing. So I'm playing with the component over B1, and I can do the same thing. And now I'm faced with two things. If B2 is better than my initial vector, let's take it and keep on. And if not, if B2 is bigger than B1, a standard proof is going to show that B1 satisfies Hermite's inequality. So if B2 is not better, that means that my B1 is good. And if B2 is better, I'm going to take that B2 as my B1, and I'm keep doing that game. Okay? So if you do that, you realize that this algorithm must terminate because I'm finding shorter and shorter vectors. But the number of vectors shorter than my initial vector is bounded. So this algorithm must terminate, and it finds you a short lattice vector. So now we have a constructive algorithm. There's just one problem. It may not be polynomial time. It may not be efficient. But the simple idea is very simple. Right? So this is where the LLL magic comes. LLL found a way to use the same type of argument, but make sure that it's efficient. So that's non-trivial. Okay? So what they do is they're strengthening this test B2 less than B1. Okay? So if we're very unlucky, maybe B2 is not so much, is too close to B1, and then we might run into problems. So if we don't want to work with projection, we can view it completely abstractly. What are we doing? By projecting over a hyperplane, we're actually looking at the lattice modulo the lattice generated by the first vector. So we're really looking at L divided by L1. Okay? So if you remember my filtration. And then we're saying if B2 mod L1 satisfies Hermite inequality in the quotient, then we can always modify B2 such that the norm is limited. And we're saying if the vector is not better, then that means that my B1 is good, and otherwise I'm swapping. Okay? So using these arguments, similar arguments, Hermite actually showed the existence of bases such that the Gram-Schmidt of organization of the bases satisfy the following inequalities. All the mu ij's are less than 1/2, and all the Gram-Schmidt ratio are bounded by 4/3. Okay? And then it's a very easy exercise to show that if you have such a basis, then B1 must be short. So for instance, B1 satisfies Hermite inequality. But you can also show that B1 is not far from lambda 1. And more generally, even though I did not define the successive minima in general, the IF basis vector is not too far from the IF minimum. Okay. So remember, so what is the meaning of this condition? So if I look at my basis with respect to the Gram-Schmidt basis, once I normalize it, I can see that this would be the first vector, this would be the second basis vector, and so on. So you can see that the mu ij correspond to the off-diagonal coefficient, and this second condition on the ratio corresponds to the diagonal coefficients. So we have two types of conditions, diagonal conditions and off-diagonal conditions. Okay. So let's start with the first condition. Is it easy to enforce this thing? So this is known as size reduction. So we're going to say that a basis is size reduced if all the mu ij's, these components over the Gram-Schmidt basis, is less than 1/2. Okay? So this is very easy. There is an efficient algorithm to make sure that the new basis is size reduced. And the funny thing is that we don't even have to change the Gram-Schmidt vectors. We're going to change the coefficients, but we're not changing the Gram-Schmidt vectors. So how do we do it? This is the algorithm. It's just a simple loop. So we just have to be careful in the order of the vectors we're working with. So you can see that to do it, it suffices to say, I'm going to go from 2 to D, and from I-1 down to 1. So I'm going to size reduce BI with respect to BJ to make sure that mu ij is less than 1/2. So how do I do it? I just subtract to BI a multiple of BJ, and the coefficient is obtained by rounding the current Gram-Schmidt coefficient. So this one is bigger than 1/2. So the rounding to an integer is going to be bigger than 1. And that's it. So these correspond to Euclid's algorithm. In Euclid's algorithm, we do a modular reduction. These correspond to this modular reduction. And then we update all the Gram-Schmidt coefficients. And that's it. So geometrically, because j is less than I, when I do this kind of transformation, I do not change the previous mu I prime j prime. So I don't change the Gram-Schmidt vectors. I only change the coefficients. So after this simple loop, you can check that all the mu ij's are less than 1/2. Okay? So this part is easy. So what is hard is this part. Okay? And that's the key idea of LLL. They realize that we shouldn't be too hard on ourselves. We should not try to make it exactly 4 over 3. We have to relax it by some epsilon. If we relax it by some epsilon, we can make sure that it's polynomial time. Okay? If not, we're not sure. So again, if I take this triangular representation of my vectors, what we're doing with LLL is working with these 2 by 2 matrices on the diagonal. Okay. So what is this LLL algorithm? So here's the definition that you must have seen before. Remember the Gram-Schmidt decomposition. So we're saying that a basis is LLL reduced if it is size reduced. So all the mu ij is less than 1 over 2. And we have this funny condition which corresponds to the 2 by 2 matrices on the diagonal. So we're saying 1 minus epsilon times bi minus 1 star square is less than this thing. So to explain this condition, what we're saying is we're looking at the norm of the pink vectors with respect, so this coefficient corresponds to this vector here, this projected vector here. So we're comparing the norm of this guy with the norm of this guy. Okay? And we're doing for every rows. So if this condition is true, so this is known as Lovács condition, since it's size reduced, you can see that each norm or Gram-Schmidt norm is bounded by this quantity. So it's exactly Hermite condition. So if Lovács conditions are satisfied, if LLL conditions are satisfied, then it must be Hermite reduced. Okay. Now, of course, this is the definition. So now the question is, what is the algorithm? And LLL is a very, very simple algorithm. Here's a 3-line description of the algorithm. While the basis is not reduced, size reduce it with the previous algorithm. And if it's not reduced, that means that one of the Lovács conditions does not hold. Okay? So if it's not the case, just swap the 2 vectors, like you're doing with Euclid's algorithm. You swap the 2 numbers every time. Okay? So here, if it fails, just swap the 2 annoying vectors. Okay? So that's one way to describe the algorithm. So that would be the iterative way to describe LLL. If you prefer recursive algorithm, you can also see it that way. You take a basis, and what do? Similar to Hermite, you're going to reduce the projected basis. Okay, so you project over the hyperplane of orthogonal to B1. And then after you reduce inductively, you make sure that each component is also bounded. So you size reduce each of the vector. Because if you only have this, you do not control B2 mod B1, BD mod B1. So you have to do this thing to control BI modulo B1. Okay. And then you have to compare B1 and B2. So if B2 is much better, you take it. If not, you stop. Okay. So that's more in line with Hermite's algorithm. Okay. So when you have this definition of LLL, there's a very useful fact that can be proved. During the algorithm, the minimum Gram-Schmidt norm never decreases. And the maximum Gram-Schmidt norm never increases. So this says something about the lattice span by the Gram-Schmidt vectors. Okay, so there is some geometrical phenomenon. And the volume of the lattice span by the first I vector never increases. Okay? So one thing also which is very useful is that the only operation that could modify the Gram-Schmidt vectors are swaps. Size reduction does not change the Gram-Schmidt vectors. Okay? So we know these facts. We can say more. By definition, you can see that whenever you swap 2 vectors because some Lovács condition fail, you can follow the Gram-Schmidt norms. And you can say something about the new Gram-Schmidt norms. So this is the important things. When you swap 2 vectors, you realize that the new Gram-Schmidt norms are inside the old Gram-Schmidt norms. So you're narrowing the width of the Gram-Schmidt norms locally. Okay. So when you do this, that's really useful to prove that the algorithm is efficient. So here's the really amazing trick of LLL. To prove it's polynomial, you consider this quantity. Okay, so the product, it's a product of Gram-Schmidt norms with different coefficients, different exponents. Okay. So if we assume that the input vectors are integer vectors, we notice that this quantity is actually an integer, so which is not obvious at all when I look at this. So how do I do it? So I write it differently. I could write my P as a product of volume. So we can see that this is the same as taking all the volume of the first I vectors from 1 to d. So each of these numbers is an integer. So P can be rewritten as a product of integers. Okay. So what happens to this potential function? When you do size reduction, we know it doesn't change the Gram-Schmidt vector, so the norm are not affected, so P is not modified. But by my local study of LLL, I know that each swap of LLL doesn't change most of the Gram-Schmidt norms except 2 consecutive Gram-Schmidt norms. But because of the way I analyze, I know that this quantity decreases by some factor strictly less than 1. Okay? So less than 1 minus epsilon, where epsilon is fixed. So that tells you that this number of swaps is polynomially bounded. Okay? So that's really Lovács' argument. So this is the main argument showing that LLL is a polynomial time algorithm. However, it's not a full proof that the algorithm is polynomial time because we also need to check the cost of size reduction. And for that, you need to pay attention to the size of all temporary variables. But if you really follow what we were doing initially with integer Gram-Schmidt, it's not difficult to prove this. Okay, so this is really the main argument. Okay. So what did we do? We saw an algorithm that finds, in polynomial time, a basis which is almost like Hermite. The mu ij are less than 1 over 2, but the ratio are less than only 4/3 plus epsilon. So this epsilon is what is changed compared to Hermite's later. Okay? And then once you have this, it's much easier to prove that B1 is a short vector, and that Bi is a nice approximation of lambda I. Okay? So if we look at what happened, if we want to reconstruct, suppose like you have an accident and then you forget everything. Can you recover the LLL algorithm from scratch? Okay. So actually, if you think about Hermite Inequality LLL, you could remember everything from scratch if you remember the following 2 things. You need to project, and that means you're actually dealing with quotient lattices. And you need to lift your projected vectors, so you're doing size reduction. If you master these 2 things, you can recover LLL completely. Okay. So if you've already seen the algorithm, this is very familiar to you. So now I want to say things which are less common. So I want to talk about LLL in practice. Okay. So in this picture, this is Lagrange, this is Hermite, and this is Lovács, and these are the Lenstra, some of the Lenstra brothers. So if you play with LLL before, and I encourage you to follow Bill's instruction in Paris, you have heard that LLL somehow performs better than what the worst case bound suggests, okay? Especially in low dimension. So I want to say a bit more about it. So what does it mean? So this bound close to Hermite's constant, to Hermite's bound, is actually tight in the worst case. Okay? So there are some input for which the output is exactly this. However, that doesn't tell the full story. So we know that in practice, for most input, this constant can be replaced in practice by a smaller constant. And that by, I mean, for any lattice. For any lattice, if you randomize the input basis, you will never find something worse than this. Okay? So this is not a theorem. This is a practical fact. Okay? And we still don't have a rigorous explanation of what is going on. So there is now some theory about what's going on, but it's not a theorem. And we don't know what is the meaning of this constant. Okay, so is it? I mean, does it have a nice form? I mean, what is it related to? We have no idea. So here's what I want to say. For instance, you take Bill's instruction. You change you can take any lattice that you want, your favorite lattice. You run LLL on it after you randomize the input basis. And you look at the size of B1 divided by the diff root of the co-volume. Okay? So this quantity is bounded by an exponential factor. So I'm writing it in logarithmic scale. Okay. This corresponds to the worst case bound of LLL. And this is what you get in practice. So in practice, you're always fluctuating around here. Okay. So it's better, but not that much better. So it's better in the sense, yes, this exponential curve is lower than this one, but it's still exponential. Right? So the only difference between these two curves is the slope of the exponential is different. Okay? And it never gets worse than this. I don't know any lattice for which once you randomize the input basis, you are beyond that line significantly. Okay? So it's always somewhere here. Maybe there's some exceptional lattice for which you're going to have a better vector. It could be here, but you're never going to be beyond that curve. Okay? But here's something more. So a couple of years ago, Venkatesh and one of his students showed that most LLL bases of a random lattice have a B1 close to the worst case. So what does it mean? First of all, for any lattice, the number of LLL bases is finite. So there's a super exponential number of LLL bases, but it can be bounded with respect to the dimension. So there's only finitely many LLL bases for a given lattice. Okay. So now they look at random lattices, and they look at all these finitely many LLL bases, and they show that most of them are bad. So what does it mean? It means that when you run the LLL algorithm, the basis output by LLL is not a random LLL basis. It is biased. It's not the uniform distribution. And in fact, later on, so Venkatesh tried to explain that phenomenon. So he has a model of the algorithm. So it's a model, it's not a proof. Under that model, using sand piles, he proved that B1 must be better than this worst case bound. But it's not a proof for LLL because he's starting with a model. Okay. However, his experiments seems to show that the behavior of LLL corresponds to this sand pile model. Okay. So this might be the reason why LLL behaves better than expected. Okay. But it's not a proof. So if you're interested in this question, here's one way to phrase it. You take a random integer lattice with respect to the previous distribution I was talking about, you take the Hermite normal form of that lattice. Is it true that with overwhelming probability, once you LLL reduce this Hermite normal form, this vector B1 is much better than what you would expect in the worst case? Okay, so that would be a way to phrase it. Other information you might be interested in is, can we guess the distribution of the norm of B1 and the running time of LLL when you do these kind of things? Okay. All right, so now I want to talk about Babai's algorithm. Okay. So this is a standard application of LLL. So this is the nearest plane algorithm. Okay. So suppose you want to find the closest vector of a target vector in the lattice. So that's a very hard problem. So instead, what you can do easily is you can tile the space by using the Gram-Schmidt parallel pipette. So here, this is B1, this is B2. This is the tiling formed by the Gram-Schmidt vectors. Okay? So that means that every point in the space belongs to one of these parallelograms. Okay? And if I identify which one it is, then I have found a lattice point such that the target minus the lattice point belongs to the initial parallelogram. Right? So how do I find this lattice point such that the difference is a point inside the Gram-Schmidt parallel pipette? Okay? So that's the nearest plane algorithm. It's essentially size reduction. So it's size reduction where I'm cheating. I'm going to view the target as a new vector. Okay? So you just compute these inner products. You round these real numbers to its closest integer. And that's it. And you take the vector corresponding to it. Okay? So using this, you can see that it's similar to size reduction. You can identify which tile T is inside. Okay? So that's the nearest plane algorithm. After that, yes, I have found a linear combination of the BIs with integer coefficient such that the difference is a point inside the Gram-Schmidt parallel pipette. Okay? So why is it useful? So this very geometric algorithm has the following properties. So if the input basis is LLL reduced, then it's easy to prove that Babai algorithm solves bounded distance decoding if the noise is sufficiently small. And this guy can be bounded, lower bounded when the basis is LLL reduced. Okay. So this is always true. This is true even if the basis is not LLL reduced. But when the basis is LLL reduced, you can lower bound this quantity. So that tells you that we can solve BDD if the noise is sufficiently small. Okay. However, if the basis is LLL reduced, you can really show that it approximates CVP up to some exponential factor. Okay, so that is less trivial. Okay, so that's Babai algorithm. Now I want to talk a bit about Gaussian measures. So I already talked a little bit about it when I was talking about my torus. So what is the Gaussian measure of a lattice point? So there are two parameters. There's a center, and there's the parameter S, which loosely correspond to a standard deviation. Okay? So this is a discrete distribution where the mass of a lattice point is going to be proportional to this Gaussian function. Okay? So if you like theta functions, you know that this is related to the theta function of the lattice. And this Gaussian measure was introduced in the 90s by Banachek to prove a transference theorem. It was also implicitly used by Maizo and Odlisko when they wanted to count integer points in ball. So this is a very useful tool. Okay. So this is how it looks like. So here would be the center. You can see that the points which have the biggest mass are the ones which are closest to the center. Okay. So you can see if you're far away, you have a very low probability of being hit. Okay. So that's the discrete Gaussian distribution. So alternatively, if you don't like this, you can see that it's the same as defining an elliptic distribution over the hypercubic lattices with a certain covariance. Okay. So this is related to what I was doing before. So remember, I was taking the Gaussian distribution over the real, and then I was saying when you fold that distribution, you get this distribution, and for a very big standard deviation, the Torus distribution becomes uniform. Okay, so there's a similar phenomenon over a general torus. If I take the linear span of L divided by L, so here it was R divided by Z, that's the one-dimensional case. So what I'm saying is that if I take span of L, I take the Gaussian measure over the linear span of L, and I take the folded distribution in the torus, we have the same phenomenon, which is if the standard deviation of the Gaussian is bigger than some threshold, then the folded distribution is uniform. Okay, so this is just a one-dimensional version of this phenomenon. So that's what is called the smoothing parameter of a lattice, is the threshold from which the Gaussian over the linear span folded becomes uniform. So that means that the Gaussian mass of the coset are all identical, all close to this quantity. So this is the Gaussian integral divided by the covolume of the lattice. Okay. So using this phenomenon, using this smoothing parameter, you can prove something very intuitive. For instance, you can say, what if I pick a point, a random point in the lattice, and I consider a sublattice of that lattice? Then using these smoothing parameters, you can show that a random vector in the big lattice belongs to the sublattice with probability 1 over the index, which is very natural. Okay? So I can say that's what you would expect. Okay. Now, if you do this, there is a very natural question. I have defined this discrete Gaussian distribution. Can I sample with respect to that distribution, right? So it turns out this was done in 2000. So in 2000, Klein introduced a randomized variant of his Babai algorithm. So at that time, he did not, so the discrete Gaussian distribution was not known at that time for Klein. So this distribution was depended on the basis. Okay. So he analyzed only the algorithm for small parameter. Okay. And 8 years later, GPV showed that if S is bigger, so if S is bigger than the largest Gram-Schmidt norms, then this distribution is no longer depending on the basis. It is statistically close to the discrete Gaussian of parameter S. Okay? So saying differently, if the parameter is big enough, I can sample the discrete Gaussian distribution independently of my basis. Okay? So it's no longer a basis-dependent distribution. It is my discrete Gaussian of parameter S. So I have a Gaussian sampler. I have a polynomial time Gaussian sampler, but only for s. So of course, if I was able to sample the Gaussian for very small s, that would mean I could solve the shortest vector problem. So that's too hard. So I can only sample vectors which are have norm corresponding to my input basis vectors. Okay, so I cannot cheat. So how does it look like? Remember Babai nearest plane algorithm, it looked like this. So how do we switch from Babai's algorithm to a Gaussian sampler? Well, you just need to replace the rounding here by a randomized rounding. Okay. So instead of having deterministic rounding, you pick it with respect to a discrete Gaussian in dimension 1. And then it's a funny exercise to show that this algorithm sample with respect to the discrete Gaussian. So if you play this game, you can show that, yeah, if the parameter is big enough, thanks to the smoothing parameter, everything becomes uniform, and I can prove that my output distribution is exactly the discrete Gaussian distribution over the lattice. Okay? So just by changing deterministic rounding by randomized rounding, by this Gaussian measure over a one-dimensional lattice, I get exactly what I want. Okay, so it's getting late, so I have a few minutes still to talk about worst case to average case reduction, which I mentioned before. So I mentioned before this I-ties result. So I'm going to show you how it looks like, and that's why I needed this Gaussian sampler. Okay. So remember, what was the problem that we had? We had this SIS problem, where you had a finite abelian group, G, initially ZQ to the n, and which we were viewing as Z module, and we were looking at the lattice formed by all the linear relations between these group elements. Okay, so we pick random group elements, and we look at all the short integer relations between these group elements. And as we saw before, this is the same as finding a short vector in a random lattice in that finite class. Okay. So what I want to show is, suppose somebody can solve this average case problem, can you use that person to find short vectors in any lattice, not just a random lattice, any lattice? So I'm just going to show you the proof for this, for the simplest case, which is ZQ to the power n. Okay. So let's take a worst case lattice. That's L. So L could be any lattice. And I'm going to show you how I can find short vectors in this worst case lattice. Okay. So what I'm going to consider is, I'm going to consider an overlattice. So L bar is just 1 over Q times L. So L is inside L bar. Okay. Now notice that you have a very simple exact sequence. So I can go from L to L bar to G. How? So it's easy to build a morphism such that L is exactly the kernel of phi. So you take a basis, for instance, and you can see what would be the morphism. So you can have this sequence here. And so how is it useful? So imagine that L is the kernel of phi, where phi is efficiently computable. You take arbitrary vectors in the overlattice, 1 over Q times L. Okay? So, of course, yeah, something I should have said. If you take a scaling of L, obviously the quotient, the torus, is isomorphic to G. Okay? So that's why this choice of G makes things simpler. So I choose the same n so that this is very easy. Okay. Now what I do is I'm going to map every lattice point here chosen from L bar to a group element by applying the morphism phi. Okay, so GI is phi of VI. Now, imagine that the sum of the xi is equal, GI is equal to 0 in the group. Then that means that this guy, sum of the xi vi, belongs to the kernel of phi. But that means the lattice point, right? So that means that if I take a lot of vectors in the overlattice, if I found a linear combination equal to 0, that means that I have found a linear combination of my overlattice vectors inside the initial lattice vector, right? But then notice that if ever the xi's are small, and if all the vi's are small, then this guy is also short. So I have found a short lattice vector, right? So there's only one problem. This looks like the SIS problem, right? But there is a constraint on the SIS. What is the constraint? What is the rule of the game? When I define the SIS problem, there is something very important that I emphasize. The group elements that you choose must have uniform distribution. So if I do this like this, how do I know that these GIs have the right distribution? So I want to make sure that the GIs, which are the maps, the images of VIs, have the uniform distribution. Then I can play this game. Okay? So the main ingredient, the technical difficulty is to make sure that those GIs have the uniform distribution over G. And that's where Fourier analysis comes handy. So it's exactly this smoothing parameter business. So we show that if the VIs are chosen from the discrete Gaussian distribution with sufficiently big smooth parameter, then the image has uniform distribution over G. So what we want is a distribution such that any mass function such that the mass of a coset is close to 1 over the order of G. And as I told you before, yeah, we can take the discrete Gaussian distribution. Okay? So if the VIs are chosen from the discrete Gaussian distribution with sufficiently large S, then this is true. This is a theorem. Okay? So that's the key step. How to transform, how to take any lattice and build the uniform distribution over the group. Okay? So this is it. This is my worst case to average case reduction. You sample short vectors in the overlattice from the discrete Gaussian, and then Fourier analysis guarantees that the images have uniform distribution over the finite group. Now that they have uniform distribution, you're allowed to use your SIS solver on this input that gives you small integers such that the sum of the xi gi is equal to 0 in the group, by definition of the SIS problem. But if this is true, that means that sum of the xi vi belongs to the lattice. So you return that vector. Okay? So here you will use your discrete Gaussian sampler. Okay? So what you can ask is, how come they are short? So you can see that here, the norm of this vector depends on the size of the VIs. But the good thing is you've scaled the lattice. So your ability to generate short lattice vector in that scale lattice is better than in initial lattice. So you can sample shorter vectors in bar L than in L. And thanks to the SIS oracle, you don't enlarge too much the norm of this shorter vector. So in the end, it does give you a short vector in your worst case lattice. There is just one problem here that I did not emphasize. I did not talk about. What is it? What could be problematic here? So here, yeah, the GI have uniform distribution. The size of the XIs is small by definition of the SIS problem. So this guy is going to be short. There's just one problem that could happen. Yes, maybe this guy is 0. So you have to somehow show that this guy is non-zero with high probability. Right? So in fact, people, what they do is they can analyze the distribution of this vector, and they can show that it's non-zero with high probability. Okay. And not only that, you can obtain not just one single short vector, you can find many short vectors, because by applying the same thing many times, you get, with high probability, linearly independent vectors. Okay. So here I only did the easy case when ZQ to the n. So I only use the fact that, yes, if B is a basis of L, once you divide it by Q, it's a much shorter basis for the overlattice. But what happens if you change of groups? So if you don't take ZQ to the n, how do you do? So we found a way to build a different overlattice such that the quotient is isomorphic to G, and yet we can sample short vectors in the overlattice. So for any sufficiently big finite abelian group, so not just for ZQ to the n, it's possible to do this. And surprisingly, the process that we're doing is very similar to LLL. So there's a way to tweak LLL to do these kind of things. Okay. So usually, I mean, finding a short basis is difficult, but if you have some flexibility, if you can change the lattice, if you allow to modify the lattice, it becomes somehow easy. Okay. Okay, so I think now with the heat wave and everything, everybody is very tired. So it's time to finish these lectures. So I want to conclude with a few questions. So here, what I was doing was I was showing you the first lattice reduction algorithm, LLL, which has been improved somehow by BKZ and other stuff. But in terms of mathematics, lattice reduction algorithms were completely superseded by other techniques if you want to optimize bounds, for instance. But for algorithm, we're still using lattice reduction techniques. Okay? So it's a question, how much can we push these techniques? And in particular, people are very interested to find out how much this lattice reduction algorithm can take advantage of special structure. So I didn't talk about the cryptography based on lattices, but I only say one thing. In order for this cryptography to be very efficient, we need to take risk. So people take lattices with extra structure. For instance, they can take ideal lattices. They can take what is called module lattices. And of course, if you add extra structure, there's a big question mark. Can this be used to attack the scheme better? So this is still a work in progress. There are some preliminary results, but we don't still have a definite answer about that. Okay. There's another question that bothers me is, so when we look at mathematical problems, this lattice reduction technique has been superseded by different techniques. Could the same phenomenon happen for lattice problems? So historically, we're using lattice reduction to solve lattice problems. So maybe that's not the right way to look at the problem. Maybe we should ignore this lattice reduction business and solve the problem differently. So that's why I was giving you this group description of SIS and LWE, because here the lattices have somehow disappeared. And maybe there's a way, maybe it's a different way of looking at the problem. Maybe there's another way to tackle these problems. For instance, you could think when you see this group description of lattice problems, it's begging for Fourier transform. But yet, we don't know how to do it. So yeah, I mean, something is funny here. And since there are young people here in the audience, I'm encouraging you to think about the following problem. Is it possible to design algorithms, efficient algorithms, to find a shortest vector, an approximate shortest vector, within a factor polynomial in the rank? Okay? And here, the rule of the game are flexible. You could try to do it quantumly with a quantum computer, or you could try to do it within sub-exponential time. So that would be a very nice result. And that's all I wanted to say. Thank you for your attention.